Welcome back, everybody. Today it is Friday, and yesterday we were working with Newton's third law, which remember, every interaction pair that we ever deal with, we have object A and B. If A pushes on B, then B pushes back on A with equal but opposite force. Okay. Now, going through that, we looked at the softball problem, and we set it up once, and we saw that, wait a second, that number's way too big, and we fixed it after the fact. Moving forward a little bit, today we have 3 examples that we're going to wind up working together. But before we can get to the examples, we need to get a little bit of prerequisite knowledge here. So we'll just make sure we're physics. I didn't change the date on the board for today, so it's the 18th, which is pretty cool. And we're going to jump right in. Okay, just so you guys are aware of the plan today, we'll see, I think we're going to be able to get through everything. Which means maybe we're able to finish a chapter today, which is pretty neat. Kind of play that by ear. But we are continuing in. This is 4.3 continued. And today we are going to jump in with a definition and our main topic. We talked about the normal force. And, sorry, we did not talk about the normal force. Just kidding. Scratch that. We were talking about Newton's third law. Today we see an application of that. And see how it fits into a variety of different problems. We are talking about tension. Okay, not the fun kind that makes dinners uncomfortable, obviously, but in a physics class, tension regarding what? When you hear tension, where in the physical world might you see this? A rope. Okay, oftentimes we have stuff that hangs or gets pulled or whatever the case is. And if you don't want your rope to snap and destroy whatever it is, or whoever it is on the end of that rope, then we need to have an understanding, at least basically, of this idea of tension. So, super easy to define. It can be a little bit harder to pick out everything with it, but we'll get practice today. By definition, super chill. We're going to say that tension is simply the force that a string or rope, and if you guys just want to write rope, that would be okay, but I'm going to be more specific. The force that a string or rope exerts. And we can even be a little bit further, because if I just say it exerts it, like if I just had a rope sitting here on the desk that's exerting a force downward, but that's not tension. What does it have to exert the force on? So maybe itself, I like that idea. But check it out. I will just take a little bit of string here. Is there a bunch of tension in the string right now? How can you tell? Okay, so do me a favor, add tension to it. Okay, right now I can feel Riley pulling on this string, right? Can she feel me pulling on anything? Now, with that, you can a little bit, right? Okay. As we're looking at it, if we pluck this, all of a sudden you can start to make like notes and you can see how tight it is and you can get frequencies out of it, which is pretty cool. But all of a sudden, as soon as we start applying force in both directions, we get tension. Our problems are much nicer than 2 objects pulling. We'll talk about tug of war at least a little bit. But pretty commonly, we're just going to look at a hanging object, because lots of different stuff hangs. And bridges, it turns out, work with this idea of tension to help support it. Lost my stylus. That was quick. Cool. All right. So, when we talk about what it's exerting a force on, if I lost the string now. What the heck is going on? Goodness gracious. Just having one of those days. Okay, we're going to see what those was pinch. Okay, if I just hang this pair of scissors from here, is there tension on the rope right now?
Yes.
Okay, what is pulling the scissors down? Gravity. What's keeping it up? The string. Be more specific though, because strings aren't forces. Tension. Which way is the tension on the string pulling? Upward. So it counteracts, right? It's acting on the object that's being secured by the string. So we'll just say exerts on a held object, or supported object might make more sense. All right. Now, there are all sorts of crazy things that we can do with tension. Maybe we can play a little game. Have you guys ever heard of a tensegrity table? Okay, so they're awesome. I'm going to make a note real quick so I don't forget, because I will. We're going to look at these after we go through this tension stuff. Tensegrity tables. They are so cool. Okay, Now, going on here, couple things that we get in our nice physics class, because we're not doing crazy mathematics in here. First thing, we work with ropes that don't have any mass. So we're going to assume that there's just no mass in our rope because that changes everything about a problem. So our ropes are massless. That is the first thing I just want to make sure that we get out of this. Okay. That is an ugly word. Our ropes are massless. Now, depending on how you look at a situation, we're going to draw a little picture here, and we're just going to suppose that we have a bucket that's just kind of hanging down. So let's say we have a hook that a rope is hooked to, and I have a rope hanging down, and I try to do it bold like this so it doesn't look like a string. And on the end of this rope, hypothetically, let's just say we have a nice little bucket sitting here. So it's beautiful. Okay, we have a rope with a bucket. If it's being held up, there's tension in this rope. Would you guys agree with that? Now, when we look a little bit closer at it, we see that there's a few different ways that we can think about it. Hypothetically, is it possible that there's so much weight that right near the middle, this rope is about to break? So like maybe it's stretched really, really thin and it's about to break. I'm going to make sure I can identify that. Almost broke. Or breaking, rather. Okay. In this situation, what would we do to cause the rope to break? You would add more force to it, right? Now, when we think about these things, there's several different forces at play going on here. First of all, what pulls the bucket down? Okay, and if the bucket's not moving, it's equal and opposite to the force of what from the rope? Tension. Now, here's the weird idea. That isn't weird, I don't think. We've seen that. Is that Newton's law? Third law? Are you sure? Maybe. Let's look at this a little bit closer. If we think about this rope, everywhere about this, we have forces fighting. Would you agree with it? Now, even with this rope, if we just look at the system itself, there is a force of tension that's doing this lovely thing. I'm going to go ahead and draw that vector. Okay. This tension is a force, and I'm just going to say that this is the force of tension, sub T, and then this is kind of counterintuitive for me, but maybe it's not for you guys. That's the top of the rope pulling on which part of the rope? The bottom. So we have the top of rope pulling on the bottom. Now, you may argue that it's pulling on the bucket, and I'd say you're not completely wrong, but if we're just looking at the rope itself, the top of the rope has to support the bottom of the rope, and since that exists and we're pulling on the same object, I'm going to claim there's another force, I'm going to change color here, of equal but opposite magnitude here. That is another force of tension. Now, which part of the rope pulls that direction? The bottom, and it pulls on which part of the rope? The top. Now, this idea, bottom on top, this idea can feel kind of strange sometimes. And the good news is that it's not crazy challenging as we deal with this. We have top on bottom and bottom on top. Is this Newton's first law right, or third law right here? How do I indicate that these are an interaction pair? What markings do we put on this picture to indicate that? We're going to dash line. So I'm just going to connect these guys with a dash line, and look at that. There's our interaction pair. Now, obviously, there is more going on here. Would you agree with that? There's at least one more force working in here. What causes the tension that pulls the bottom of the rope from the top? The bucket, and more specifically, what force does that bucket use to do that? Gravity. Okay, if it's not moving, we are net force of 0, yeah? So it means that those are exactly equal but opposite. Where on the rope, and you're going to answer, I assume, right here, but where on the rope would you feel the tension? So if it's breaking, we're assuming it's going to be right here is where it's going to break. But is that always necessarily true? If two people pull really hard on a string, is it always going to break right in the middle? Is it possible that it breaks almost all the way towards one end or the other? Yeah, so if we think about that, that tension is felt where on the rope then? So maybe it's the weakest. Eventually it'll be the weakest, it'll start to concentrate. But if I were to measure the tension here, would it be the same as the tension down here? Is the same as the tension right here? I think so, right? Otherwise, guitars and musical instruments, they wouldn't stay in tune. You'd have to hit it in the perfect spot every single time. Okay, going through this. One big comment, this bucket's not moving. What do we say it's at if its net force acting on it is 0? Doesn't move up, doesn't move down, and I can't remember if it was this class that we mentioned it. Before we're going to define it, and if it's a repeat, that's my bad. Before this breaks, before rope breaks, we have what is known, and I'm going to sneak down to the next line, equilibrium. Have we used this word in here? Okay, I just couldn't remember. All right. As we're looking at these, we just needed this idea of tension to be able to jump right in. I'm not worried about looking at a tug-of-war example right now. I think we should just jump right into doing some examples. Cool. So, check it out. There's a hole punch over there if anybody decides they want a binder. But we're going to work a few examples together. If you would rather do this in your notes, totally cool, but I have worksheets for everybody. All right. Now, in dealing with these, we're just going to jump right in. And Rafa, if you're watching this, I'm not going to write the examples here. If you look on the Google Classroom, and I'll just show everybody this. And I haven't decided whether I'm going to put both of these there or not. I don't even have Google Classroom open. What am I doing? Okay, in Google Classroom, what I've done is I've shared a link with everybody for physics in-class examples, and I'm just going to make a running list so that you can go back and look at all the examples that we've done. My question for you, and I can do both or one or whatever. Right now, if we open this up, you guys can't edit it, and I don't want you to be able to edit it, but you can see it. Would you rather I do it with these ones or with a key? Like, because I'm going to do the problems with you, I think. That's kind of the intent. Do we need a key here or just the problems themselves? Because you're going to have the key. Say that again. Which one's okay? Okay, deal. That's easier for me, so I'm cool with that. All right, so let's go ahead. I want you guys on that first problem about the 50 kilogram bucket, verify for me the velocity is 3 meters per second and it doesn't say meters per second squared because mine original one did. On problem, it doesn't have a number. The first problem there is a velocity 3 meters per second or meters per second squared, does it say? Okay, good. I made the edit then. Cool. All right. I want you guys, spend a moment. I want you, to draw me this picture real quick. Over here on the side margin, draw this situation, and it can be a bad picture, but we're going to make sense of our free body diagram as well. Read through the problem, try to draw a picture, and then we'll work on the knowns and stuff together. I'll give you guys a moment. I want to hear lots of talking about the physics, preferably. So we have this. Which direction is positive for us? Down or up? Up seems reasonable, so we'll just say up is positive. And then only other thing that I would add to this is I know that the acceleration is moving upward. You do not have to use the vector notation. It's cool if you don't. I'm going to try to be better about it. Okay. What do we know? So let's try that a different way. Sean, give me one of the things of known information that I have. Okay. So be really careful. It doesn't specify here, but we're told that after it's lifted 3 meters upward, the velocity is now 3 meters per second. It doesn't explicitly state it, but what is it reasonable to assume it started at? 0. So I like that you identified the velocity, Sean, but let's say that our initial velocity is 0 meters per second, which means according to this problem, what's our final? 3 meters per second. Okay. Fern, give me another piece of known information that we have. I know the mass of this bucket. What's the mass? So mass M is 50 kilograms. That's a heavy bucket. Like, really heavy bucket. All right. What else? Abigail, anything else that we know? Okay, how would you like me to write that down? So less than that. Here's, like, I like your idea because you're on the right track. But we're actually trying to see if the rope will break, right? So I think that what you just identified is until we know whether or not that tension is greater than that, we don't know if it breaks. Would you agree with that? So I think what we're actually trying to find out of all of this is to determine if the rope breaks, we just need to find the force of tension that's in the rope. So definitely something we need, but we know it has to be greater than that if it breaks, right? But we don't know it yet. So that's what we're after. Good catch though. Totally, anything else I know? How on earth would I write that this thing lifts or changes its position by 3 meters? Change in position. How do I write that down? What's my label? Delta, not T. Delta X. Okay, it's 3 meters. Anything else that we know? Ooh, that was the last one I think I needed. Gravity G. What's the value of gravity? Negative 9.8. And units here, what do you guys think? I'm cool with newtons per kilogram. If we have to wind up changing it, is that okay? What's equivalent to newtons per kilogram? Meters per second squared. If you're ever wondering about that, just think that this number is also 9.8 meters per second squared. We just changed the units. Okay. Well, that's a lot of givens or known information. We're trying to find the force of tension. So we need a way to be able to connect all this stuff together. There might actually be one more known. Is there anything else that we don't know that might help us in finding the force of tension? So I'm going to spoil it. Yes, but we won't notice it for a minute. We'll figure it out here pretty quickly. All right, so we're trying to find the force of tension in this rope. Let's go ahead and knock out some stuff. Okay. I'm already stuck. Golly. As we look at it, can you guys think of any equation that might have the force of tension? Because if we want to actually find it, we know the mass. What don't we know? So we don't know the force. You're right. We know the mass. We don't know the force. How do you find force according to Newton in rule number 2? Mass times acceleration. Anybody know how quickly this bucket is rising? Or how fast it's accelerating? So careful. Easy thing to fall for. It is, I'm going to make the claim it is not accelerating at 3 meters per second. What is 3 meters per second? It's its velocity. So we need the acceleration of the bucket in the end. So maybe we'll just go ahead and put that here as well as we're thinking it out. Because if I just tried to use MA for this, I don't have enough information to solve it. So it's a good thought. We need another equation though. How many forces are acting on this? 2. Now, is there any special notation that we use to represent that, hey, this is all the forces acting together? Oh, it's a net force. Every single time, I'm not going to say, let me take that back. A lot of the time, if we don't have a good way to jump into the problem, it's that idea of net force. So if I wanted to find the net force, F net, what forces would be put together or summed up to get this? Good. I'm going to change the order on it. Force of tension plus the force of gravity. Do you guys agree that those are the only forces acting and that's going to give us our net force? I don't know what net force is yet, but we're going to find it. Okay. What are we trying to solve for though? Force of tension. Can I rearrange this equation to at least get a good step in that direction? How do you solve this for the force of tension? F sub t would be equal to what in a literal equation, which means no numbers yet? So, yep, what would I subtract from both sides to get just force of tension on one side? I have to subtract gravity from both sides, right? So I am just going to rearrange this a skosh. The net force minus the force of gravity then must be the tension. And I can see mathematically that it makes sense. Everybody still on board? Okay, it's here, though, we're going to go one step further. And I'm going to put a 1 next to this so we can reference it later. If you would rather, so this is going to be equation 1, and I will reference it. If you'd rather I go with something else, I'm cool with it. If we want to use like Greek letters so that we don't have any chance of confusing this one with something else, we can do that. Should we call it equation alpha? Let's get wild. Equation alpha. I can't control Z on this, and I hate it. All right. Equation alpha, then we'll call this. All right. This is just a reference for later, okay? All right. Can we substitute stuff in? Like, I don't know tension yet. How do you find net force? Like, forget about the fact that it's net force. Do we know the mass? Okay, so it's just mass times what? Okay, minus, what's the force of gravity? How do you find the force of gravity? Ooh. Turn with your neighbors talking, I'm calling somebody random so I don't just get silence looking at me. Shouting at me? I don't know the right language for that. We've done a bunch of force of gravity. Is it really any different than net force? Louder. Mass times gravity. Okay. All we're doing is we are rewriting this in a way that here in a minute we'll be able to make sense of it. Do I know M and G? So still the only thing that I don't know is acceleration. Okay. At this point, I could plug in for M and G, but I can't solve for A yet because I don't know what the force of tension is. We're going to take a side trip because I now realize that, man, we really need this acceleration. I'm going to change color to make like an intermediate comment. We need acceleration. And if you'd like, we can call it the net acceleration, like the whole system. But because there's only one thing, I'm not going to bother writing A sub net. All right. Well, gosh. We have all this information over here. How do we get acceleration out of it? We don't know how much time it takes, which means out and out. Hey, we could use equation 3 right here, right? Let's try it. I know that the acceleration of this system, A, is going to be equal to VF squared minus VI squared over 2 delta X. These are going to keep coming back. I have to add Newton's stuff on here still. Cool. Do we know all that information? Man, that's pretty neat. Find me the acceleration real quick. Using all this known information, I think we have everything that we desire. I'm going to say dot, dot, dot to say some stuff happens. And I'm going to let you guys calculate this out. At first step, do you guys need a little bit more time to do this? Did you have to use a calculator? Okay. 3 squared is 9 minus 0 squared is still 9. Over 2 times 3 is 6. Do you guys agree it's 9 over 6? Okay. Does this simplify? You could call it 3 halves. But because we're in physics and not math, and this pains me to say it, decimals are probably a better way to go. What's 3 over 2? 1.5. Okay. 1.5 what? What are the units that I get for acceleration? Meters per second squared. Now, we don't normally do it, but is there another one that I could? What's the same as meters per second squared? You could use newtons per kilogram. Okay. Now that we have acceleration, I'm just going to say that, check it out. Can we plug this value for A into equation alpha? Because the only thing we didn't have was this acceleration, right? So we'll just make a little note. Now, plug into alpha. Okay, so working up this direction, and I'll go back to red for this. If I'm doing this without a calculator, because I don't have one in my hand right now, anything that I could factor out of these two to make the calculation a little bit simpler? I would factor out the mass. So you do not have to do this if you just want to plug and chug right through it. But in my mind, this looks a little bit easier. If it looks harder to you, don't do this. You can straight up use ma minus mg. I have just taken equation alpha and factored out the mass to make it a little nicer. So let's just see if we can get it. What's the mass that we're dealing with? 50, and I'm going to make sure that we get this knocked out. Kilograms. What was the acceleration? 1.5, and we'll do meters per second squared. Time, or minus, I'm sorry. What's the gravity? Negative 9.8, which means I'm going to change this to a what? Plus 9.8. Okay, we'll do that. Let's see, and that's in newtons per kilogram. Okay. Does everything work out unit-wise? What do you guys think? Why? Convince me of that. Kilograms times meters per second squared. Can we subtract these? Because that's what's happening here, right? Or add, sorry. Are these like terms that we can actually deal with? They don't look like it, but are they? Because give me another way that we could write meters per second squared. Hey, it'd be newtons per kilogram times newtons per kilogram, right? And then as I'm looking at it, I see that and that would divide out. What's the only thing I'm left with? And how is force measured? Hey, we are in newtons. This is a pretty good sign. Okay, I think, not think, this is 50 times what? 11.3? Ooh, I don't know what that is, but somebody's going to be able to hook it up. 565 newtons? Awesome. We're done, right? We just found the force tension was 565 newtons. That's the end of the problem. No. Why? Oh, man. All of a sudden, we look back at the problem and say, it has a risk of breaking if it's above 525 newtons. Are we guaranteed that it's going to break? Not necessarily. And the language there, just because if it said the rope will break if it exceeds this, then yes. It might break, right? We're in dangerous territory at this point. How would we write this statement then? The rope is what? Boom. The rope is at risk of breaking. Now, if I ask you to justify further, and I'm not going to write this, why is it risk, or why is it at risk of breaking? How do we come to that conclusion? Because we are more than 525 newtons of force within our rope. Cool. This problem is pretty involved, and remember, it's going to keep throwing these things back in. Super hard, super easy, somewhere in between. Okay. I want to give you guys a head start. I want you to work the second one as well. Cool. We'll pause that. So we now have a picture with this problem. We have a block hanging by massless rope, which is nice. I don't love this bottom force that I've drawn, so I'm going to try to fix that one. What do you notice is different about the two different free body diagrams that I have on mind? Anything change between these? Why is it smaller on my top free body diagram? Why is that reasonable? So not a bad. I like hearing you guys think. Talk it out. Talk with your neighbors. It's correct, just so you know. Why did I draw the force of gravity? Whoa, am I backward? Oh boy, it's not correct. I lied right to your faces. I'm gonna switch them around. Why would the top one be bigger? Whoops. Why is there more tension? Oh, there's more weight, right? There's more mass happening here. So that's my bad. There's that one and that one. We'll say force of tension on A and the force of gravity on from block A. And then down here, we have the force of tension and the force of gravity. Okay, my bad. Sorry about that, guys. Now, we could be more specific. Are there different forces of gravity acting on different parts of this problem? Like there has to be. The top rope has more weight hanging from it. Okay, let's check out our knowns. I'm going to show you. No, I lied. I'm going to give you a minute. I want you to work this problem, and we're going to compare it to how I do it. Cool. Talk it out. Give you like 5 minutes. I'm going to give you a head start. These things take a little practice. We need an equation. So we don't have any acceleration to deal with because our net force is 0. We can't really find the force of tension with accelerating or anything like that. Gosh, if only there were possibly a way to jump into this problem. When we had struggle starting the first one, what do we kind of rely on? Right off the bat, it's a good strategy. If we don't have a good jumping in point to deal with these things like independently, I think we talked about the net force, right? Okay, I know that F net is equal to what? And let's do, which object are we looking at first, A or B? B, so bottom rope. Bottom tension. A, sure, let's do A, that's fine with me. Okay, as we're looking at this, let's do block A first, the top tension. So I will split this up into work. Let's do top rope. All right, I know that the net force is equal to what? What are the two forces acting on this top rope? Gravity and tension, right? Okay, what did we say net force was? 0. So do you guys agree if I say that the force of tension, because this is a 0, I'm skipping one step, is exactly equal to negative the force of gravity? Angel, thoughts? Did I lose you there for a second? Okay, so check it out. I will add this other line in. You don't have to. If you're cool with that, like it's up to you how much you write. I know that because it's not moving and there's no acceleration, then the 0 newtons of force is going to be equal to the force of tension plus the force of gravity. Are you cool there? Help me solve for the force of tension. What would you subtract from both sides? Good. And here we are. Now, I don't have the mass and the acceleration of the object to deal with the force of tension because it's not accelerating. Now, we do have one more little piece to our advantage though, because rather than thinking about gravity as just a cause for acceleration, you can think about it as a cause for force. And that's the change in units that we use. How do you find the force of gravity? So it's mass times acceleration. Let's use a different word instead of acceleration. Gravity, or gravitational strength. And it's the same idea, but because we're not moving, I'm trying to avoid calling it acceleration. Just the force of gravity. Okay, do we know the mass and the force of gravity? So let's see, that's negative. And then here's the trickiest part of this problem. On this top rope, how much weight or mass is it supporting? 5 here. Does it also have to hold up this one though? It does. So how much total? 10. There's 2 masses being suspended at the end by this rope. So we have 10 kilograms times, what's gravity? Negative 9.8 newtons per kilogram. And maybe I've just had a change of heart and I will start including units in here. I can't decide what's easier. Negative 10 times negative 9.8. I think it's 98 newtons. Okay, without getting too crazy. Do you think that we can work out the next problem without doing as much work? The second part of it. Is it the same strength of gravity?
Yes.
What's the only thing that's changed? The mass. Instead of holding up 10 kilograms of mass, that bottom rope holds up how much? So half the mass. If we think about it, there's no squares or anything like that in my equations for force. What do you think the force of tension on the bottom one is going to have to be? The force of tension on the bottom should probably just be half of the top one. What's half of 98? 49 newtons. Boom. We have them. Should you always, And then let me, nope, not even gonna say it. Okay. How would you write this sentence? So, and I could only kind of read your lips and hear a whisper, but what I try to avoid doing is I don't love answers if they're just say something like, the force of tension on the top is 98 and the force of tension on the bottom is 49. That's a natural sentence to write. Like, it's not a bad idea. It just doesn't add anything to my context here. I would change this just a little bit. Tension produces a force, right? Okay, the top rope pulls upward with how many newtons of force? 98. Good. With 98 newtons. And the bottom upward with how many newtons?
40.
Good. Now, it may be nitpicky here a little bit, but this context tells me that you understand that it's the forces generated by the tension that are pulling this block upward to counteract gravity. Cool. If you write the other sentence, I'm not going to destroy you for it, but try to be more specific and clear with your context. Okay. Last one. How's it going? Were you able to get it? What'd you get? 0.9? 0.9 what? Okay, cool. Homework is 32 through 38. I want you guys to start it. Everybody else, verify for me before I throw you into the homework as well. Try the third one. And I'll write it on the backboard for you, Tully. Cool. Let me set it up so that when you leave, we're in a good position. What do we know? I saw like everybody had already written this. Mass is 42 kilograms. I agree with that. Anything else? Force. So we know the force of the gravitational strength is negative 9.8 newtons per kilogram. Anything else? What's what force? So we're worried about when the force of tension is what? 450. So we're just trying to check here. I think that if we're trying to find the acceleration that it's at 450 newtons, we have that value, right? Anything else? I don't think so. Okay, what are we trying to find? Now, when we talk about acceleration, remember, we're using A and G differently because they're different meanings. My suggestion, and this is the last thing I want to say, class is over, but you would probably benefit from this. I would jump in with this problem. What is net force equal to in this? The force of tension plus the force of gravity. Is this 0 this time? How do you know it's not 0? It's accelerating. Okay, we are going to be speeding this thing up. Because we're accelerating, this is not 0. I would suggest Newton's second law to help you through this. Cool. Try it out. I will see you cool cats and kittens on Monday. So your homework, finish the note problem. That's it. Nope, we'll just finish that problem. That's your homework. Yeah. So F net, I'm just trying to get out of this. So you have 450 equals mass, acceleration plus gravity. I'm cool with that. You just changed it to plus, right?
Yeah.
And then you divided by, how did you get to 0.91?
I divided by 42 and then subtracted it.
Cool. Good with that. Yep. Write me a sentence and you're cool. Bless you. What's up, Bam Bam? Okay. Go ask the office real quick. Because I don't know that one. Go ask.